The chain rule is one of the rules in calculus that we use to help us differentiate more complex looking functions, and it relies on the fact that there are some functions that can be rewritten as composite functions. Now the chain rule looks a bit complicated here if you want to pause it and read through it, but the idea is that if your function looks like two or more functions inside one another, the way to derive it is to first derive the outer function and then multiplied by the derivative of the inner function. So I'm going to explain how that works with two examples, and the process I'm going to use is something you could keep on using throughout, unless you become very comfortable with using the chain rule. So if I have this y equals to 3 minus x cubed, I know I said composite function and this doesn't look like a composite function, but let's think about it. I can split this into two main operations or two main functions. One could be 3 minus x, that could be one function, and the other function could be just cubing this. So if I want to rewrite this, I can say that f of x is 3 minus x, and I could say that g of x is x cubed. So now if I want to do a composite function, what I'm going to say is this 3 minus x has to be inside this x cubed. So I could say g composite with f of x, or g composite with f of x. So what this tells you is take this function f and put it inside the input of g. So instead of f of x, I'm going to write 3 minus x. Well, what does my g do? My g takes my input and it cubes it. So I'm going to take my input and I'm going to cube it. Okay, so it's basically this one. But what I've done is I split it into one function and then this is the other function. And that's what you want to do. Now it looks complicated, but actually you can, for some functions, it's really easy to see how you want to do it. So the way we're going to actually start differentiating is to identify this first inner function. So I'm going to call it u, and I'm going to say it's 3 minus x. So I'm going to rewrite my first function. I'm going to say instead of it being equal to y equals to 3 minus x cubed, I'm going to say it's y equals to u cubed. Now, if I give you this, it's quite easy to differentiate. You're just going to be like power times coefficient, reduce the power by 1, quite easy. But we don't want dy by du. We want dy by dx. So in order to find dy by dx, what you're going to do is first, so this is what the chain rule is, but let's translate it. To find dy by dx, which is our original function, what you're going to do first is find dy by du, which means derive this new one that we found, multiply it by the derivative of the function u, which is this one, u equals 3 minus x. So it's going to be the derivative of this multiplied by the derivative of that. So this is we're going to find the dy by du of this, and we're going to multiply it by du over dx of this one. If you want informally, it looks like I'm canceling these out and I'm left with dy over dx, but I'm going to explain how this actually works out. You can think about this in your head if you want to, as in like, oh, I'm canceling the u out, so this works. And it sometimes helps students, but I'm going to explain why this mathematically is not true, but we could still think of it that way. So let's do it. So I'm going to first find the derivative of the du by dy, which is 3u squared, so 3u squared. And then du by dx is the derivative of this u function. So remember, whenever you have the letter in the numerator, that's the function you're deriving. So the derivative of this part is just going to be negative 1. So that's negative 1, and I'm multiplying them together. If I simplify it, that's negative 3u squared. But I want dy over dx. I don't want the u in there. U has nothing, it shouldn't be there. So, well, we've just derived it, so I can bring back the 3 minus x in here. So I'm just going to replace the u with the actual original what the function is, which is 3 minus x. And that is basically the derivative of the original function. Now, once you're more fluent, you could do something like, oh, I'll take the power times the coefficient here and multiply it by the derivative of the inside, which is -1, but keep the inside, which is what this is. So differentiate the outer function, keep the inside, but multiply it by the derivative of the inside. So it looks a bit complicated, but it's something we use quite often. If you just follow this kind of substitution method in the beginning, and then it's easy to continue. So another example, something with a square root. So let's say I have this square root of 7x cubed minus 2x. So if I want to separate it into two functions, I could say that u is equal to the 7x cubed minus 2x, which means that my y is now u to the power of a half. So now this I can actually derive. So hopefully with a few examples, you'll be able to deduce how you can rewrite your functions and do a substitution. It's not something I'd expect you to do immediately, but it's so it's useful to see a couple of examples and try out on your own. So now I'm going to use the chain rule. If I want dy over dx, I'm going to first do dy by du and then multiply by du over dx. And again, you can think of, oh, I'm canceling out the du's here, but you're not technically doing that. So I'm going to do dy by du, which is half u to the power of negative a half. So that's the y part. And then the derivative of du over dx is basically 7x squared minus 2x. So I have my two sections here. So I'm going to multiply and simplify them. I did a bit of algebra here that I skipped over, but basically this I can bring down to the numerator because it's the power of a half. And then this will basically multiply with the 1. So it's just going to be in the numerator and 2 stays in the denominator. So 2 stays in the denominator, u is negative, so I'm going to reciprocate it, and then this just multiplies with the 1. Remember, there's a multiplication here. So then I can replace the u with my actual function, the 7x cubed minus 2x, and that's what I'm left with. And instead of a power of a half, I'm going to replace it with the square root. So this is the derivative of the function. Quite complex, and it's not something you would have done if you just rewrote this as to the power of a half, especially that you have x's inside. The only time you would be able to do it is if it's in the form of like y equals to x a half or something, or maybe you have just numbers inside the root, so that would be doable. Or maybe you have something like x cubed, so there's only one x in there, but you don't have a whole function inside. If you have a full function inside, like a more complex function, then you have to use this chain rule process. So just to quickly do a few minutes on explaining how and why I explained it's informally, it's like canceling out the u's to be left with dy over dx. But that's technically not how it's done. I'm just going to explain the reasoning behind it. So it's not us canceling the du's, because these are not fractions. The dy over du or du over dx, these describe the rate of change. So how y changes compared to x, how y changes compared to u, how u changes compared to x. So in order to link those relationships, think about it as if y changes twice as fast as u, so this describes this derivative. And u changes twice as fast as x. So if y changes twice as fast as u and then u changes twice as fast as x, it means that if I jump from y to x, y changes 4 times as fast as x. And that's what kind of we're doing with the whole canceling out the u somehow. It's that you're linking these changes together. This chain, you're creating this chain from y to x. So it's like creating this chain from y to x, but there's a u in between. That's like there's a rate of 2 change, which means there's a rate of 4 change here. But in order to get to the rate of 4, sometimes it's easier to try the rate of 2 and then another rate of 2 in order to get from the y to the x. Hopefully this was clear. Mostly you're going to follow the same steps of substituting u and then finding the derivative of your new function times the derivative of your substitution function, kind of roughly speaking. And then that will help you find the derivative of the whole thing. But if you just remember this formula for the chain rule, it will actually help you find the derivative of the whole function.